Okay, so last time we finished up talking about acids and bases, so we're rolling into really the next sort of part of the class, if you will, I guess. We're rolling into the organic chapter, so organic chemistry. So as we talked about at the very beginning of class, those first chapters are really more chemistry, calculations, and these type of things. Here we will be getting into really you probably won't pick up your calculator in any of these chapters at this point. So that could be a good thing or not a good thing, I suppose. It's going to be a little bit more naming, a little bit more, I say, memorization, understanding, sort of drawing some products of reactions and stuff like that. So similar to kind of like Lewis structures, a little bit different, but kind of similar. So it's going to be more of that sort of focus here on our organic chapters than again calculations. So I don't believe there's even one calculation involved in any of these organic chapters or anything at this point. So let us get going on the organic. And again, these notes are up there on the Canvas page, obviously, where all the other ones are. So we're going to start here in chapter 11 with sort of an introduction to organic chemistry. And we're going to talk about some types of organic molecules. So let's talk really what are organic compounds versus maybe some of the stuff that we've been talking about up until this point. So organic compounds, this is pretty much the first sentence of any organic book, usually right about there. It's really the study of carbon. So the basis of organic chemistry is really carbon-based compounds. The basis of sort of how organic molecules are, the kind of connection that we typically have in organic molecules are carbons attached to carbons. Attached to the carbons are usually hydrogens. And in addition, along the way, making up some different, what are referred to as functional groups, which we'll talk about obviously in this chapter and some other chapters as well. Some of these different functional groups are kind of made up of what occurs when we basically kind of substitute out, get rid of some of these hydrogens. So along the way we will see carbon binding to other types of elements, but the basic sort of organic guys, carbons and hydrogens. Also, carbon can eventually get into some oxygen binding, nitrogen binding, sometimes by replacing some of the hydrogens. Sulfur will actually see some, and so forth. So, depending on sort of what comes in place of that carbon and hydrogen sort of bond, as to what we end up with in terms of the type of organic sort of compound that we are looking at. What really determines what type of organic compound we're looking at is what is referred to as a functional group. So this is really the bond, if you will, that basically determines the type of organic molecule we're dealing with. So we'll see some examples as we go through these different organic chapters. For example, the basic carbon-carbon single bond is a group of compounds, as we'll see in this chapter, which are known as alkanes. While if you have sort of a oxygen-hydrogen bond sort of involved, that's a group of organic compounds which are known as alcohols. And there's some slight differences as to how we get these guys. We'll talk about how we name these guys as well, but it's the part of the molecule that basically represents what type of organic guy you're talking about. The basis of carbon and hydrogen bonds, as we'll talk about here, if you remember, the carbon-hydrogen bond is a non-polar bond, which means we expect electrons to be shared equally. The carbon-carbon bond is also non-polar. And what that means is most organic compounds, or a lot of organic compounds, are non-polar. It doesn't mean they can't interact with water. We'll talk about some things that allow them to interact with water. But a lot of the basis of it is sort of this non-polar relationship with carbon. Now, organic compounds are made up of carbon and hydrogen atoms, as I mentioned. Really important about carbon is it wants to make 4 bonds, and only 4 bonds. And I put only because as we start drawing some of these organic compounds, people like to lay on the bonds to carbon like there is no tomorrow. Just keep on throwing as many bonds as they could kind of throw around the carbon. And very important thing to remember, only 4. For the most part, they all will be bonds. And that's a very important thing to sort of keep in mind. Again, I exaggerated there on the left there, but although I have seen some drawn like that actually. But for some reason, especially in organic chemistry, when you're drawing these things, people just like I said, just to kind of keep piling on that bonds to carbon. So carbon has that 4 valence electrons, like we talked about with Lewis structures. It wants to make those 4 bonds. It wants to kind of continue to do that until it kind of has 4 bonds around it. As I mentioned earlier, other elements will kind of come in and bond with the carbon. Things very commonly in organic chemistry are oxygen, sulfur, nitrogen, phosphorus. The halogens, that's group 7 on the periodic table. That's your fluorine, chlorine, bromine, etc. Organic dyes are typically found in a lot of things, including gasoline. We might have talked about it earlier in the sort of solution chapter, but gas is essentially nothing more than just a super long chain of carbons attached to carbons and hydrogens attached to them, much longer than what I'm drawing here, but it just kind of keeps going and going and going. Now, the form of organic compounds are written with carbon first, followed by hydrogen, and then other elements. So when we write sort of molecular formulas, we usually always start with the carbon, then however many hydrogens, and then if there's other elements in sort of the molecular formula, you kind of put those guys next. Now, some properties of organic compounds, and by the way, when we're not talking about organic compounds, some of the stuff like ionic compounds and stuff like that, what we talked about sort of previously, those guys are sometimes referred to as inorganic kind of compounds, like ionic compounds and things of that nature. But organic compounds typically have covalent bonds because it's basically made up of bonds between carbon and hydrogen. They're both nonmetals. So that means we're sharing electrons here. Also, because they are essentially nonpolar in terms of intermolecular forces, they're pretty much using dispersion forces a lot. And if you remember when we talk about intermolecular forces, dispersion forces are these sort of temporary forces of attraction between different molecules. And because those are relatively weak, that means that they typically have low boiling points and low melting points, organic compounds. A lot of organic compounds are very flammable. They're oftentimes, as we talked about, with types of reactions. For example, methane here, which is our simplest organic guy, plus some O2, CO2, plus some water, undergoes combustion reaction very, very easily. Maybe a little balancing here, perhaps 2 there. And this is again gives off flame, gets off flammable. A lot of the very small beginning organic compounds, things like methane, things like propane, things like butane, these are all organic compounds. You're probably familiar with a lot of those guys. They are very flammable type of compounds. They are typically not soluble in water when we talk about organic compounds. Again, because of that dispersion forces, remember water is polar, which means it's going to try to use hydrogen bonding. Hydrogen bonding, dispersion forces, as we talked about, over the long period of time are not going to be able to interact with each other. They will for a short period, but as we talked about, I think earlier when we talked sort of about solubility, eventually that sort of oil layer will kind of float to the top. And typically speaking, if you have sort of a test tube, the organic layer is usually on the top and the water layer is usually on the bottom, sometimes referred to as the aqueous layer. And again, that's usually how they separate out. Again, they really don't mix because they're trying to use different types of intermolecular forces. And again, they're not going to be really compatible with each other over a long period of time. Now, many inorganic compounds have very high melting points. So things like sodium chloride, right? So something like sodium chloride, which is salt, that is held together by a very strong electrostatic attraction, right? Which is that fancy way of saying positive and negative guys attracted to each other. That very strong attraction means that if you've ever sort of heated like salt water, eventually when the water evaporates off, if you continue to heat the sodium chloride, it typically will just start to melt, and at a very high temperature, really high temperature to try to get it to boil and stuff like that. You know, it doesn't really happen under kind of normal conditions. And that's opposed to sort of organic compounds, because the difference is in an organic compound where you got, like, say, our methane going to our methane. So two methane molecules. Again, they're using that dispersion forces, which is that intermolecular forces that we talked about. Intermolecular forces, again, are the forces that hold together one molecule with another, and that dispersion forces are really weak type forces. And because they're very weak forces, it doesn't take a lot to kind of break those molecules apart from each other, and thus usually are kind of flammable and also can go into the gas phase really well. A lot of organic molecules are sometimes referred to as being volatile. Volatile basically means that, you know, they can pretty much enter the gas phase pretty easily. They could kind of go from liquid into the kind of the vapor or gas phase relatively easy. And again, that's because they're held together by these really weak forces between, you know, different organic molecules. Any questions on that so far? Here's a table from your book that again compares our inorganic guys, like something like sodium chloride, to our organic guys. And again, here's some, you know, some of the major differences, you know, between them. Covalent bonding means sharing electrons. Ionic bonding, no sharing of electrons, but that really strong electrostatic positive negative cation anion interaction. Typically, they are non-polar, the bonds in organic chemistry. Most of these guys are ionic bonds. And again, you can see low boiling and melting points. Again, because of that dispersion forces being very weak between two organic molecules, doesn't take a lot to melt it, doesn't take a lot to boil it, as opposed to super high values here when we talk about ionic compounds. That's again why we typically, right, 1413 degrees Celsius is what you would need to boil sodium chloride. And obviously, we never get anywhere near that, which is why, under normal circumstances, right, you take some salt and heat it, you're not going to get it to obviously go into the gas phase or start to boil. Very flammable are organic guys. It burns in air through combustion reaction. Not very flammable or inorganic compounds. Solubility in water, again, no, because of that dispersion forces. Again, water using hydrogen bonding, and it's not going to interact really well, but works really well with something like sodium chloride, which is an ion. As we talked about, basically water can very easily surround something like sodium ions with the negative side of water, while if you had chloride ions, the positive side of water, which is the hydrogen that we talked about, will basically surround that ion. So these are the very kind of differences that we typically see in organic versus inorganic sort of compounds. So let's talk a little bit about some of these differences and decide, are these inorganic properties or organic properties? It has high melting points. So very high melting points are inorganic guys. Again, because they're held together by really strong electrostatic attraction. Remember, electrostatic attraction is really an intramolecular force, and that is always stronger than any intermolecular force, like dispersion forces, hydrogen bonding, dipole-dipole interaction, like we talked about. Not very soluble in water. Again, that's going to be our organic because they are typically nonpolar, that carbon-hydrogen bond. Again, a reminder that the carbon-hydrogen bond, the change in electronegativity value is 0.4. 2.5 and 2.1, the electronegativity values there. Remember, from 0 to 0.4, that results in a nonpolar bond. And again, that's really your basis of organic compounds. It has a formula CH3, CH2, CH3. That is all carbons and hydrogens there. That screams organic type of compound. Has a formula magnesium chloride. Magnesium is a metal. Chloride is a non-metal. That should also scream to you that is an ionic compound, which means it would be inorganic. Burns easily in air. That's organic, as we talked about, going through those combustion reactions. And has covalent bonds, also organic. Again, that is, for example, methane. I think we probably drew it when we did Lewis structures. That is non-metal, non-metal, sharing of electrons between those guys. Any questions on that there? Okay, so let's talk about sort of some of these organic compounds and some of the structures that we commonly see when we draw them. And, we're going to kind of start with, like I said, sort of alkanes. We'll see that in just a second. But when we talk about organic compounds, sometimes they are referred to as hydrocarbons. And much like the name implies, it means it has hydrogen and carbon, basically, is what that refers to. So hydrocarbons are really organic compounds that basically contain those two things, both hydrogens and carbons. As I mentioned before, this is super important in organic chemistry. It's all about carbon and wanting to make those 4 bonds, as we see here in methane. Sometimes we have guys which are known as saturated hydrocarbons. What does saturated hydrocarbons means? Basically, saturated hydrocarbons mean that you have kind of the maximum number of hydrogens that you should to a carbon. Basically, they are guys that contain only single bonds, which is the organic group known as alkanes. Alkanes have a functional group of the carbon-carbon single bond. This guy here is an alkane. It has the maximum number of hydrogens attached, which is 4. This guy here is all carbons, all single bonded. Each of those carbons have a maximum number of hydrogens that it could attach. Now you might be asking, the guy on the bottom only has 3 hydrogens attached, and that's okay because in this particular case, it has 1 hydrogen attached, 2 hydrogen attached, 3 hydrogen attached. And that really is the maximum amount of hydrogens this carbon could have because it has its 4th bond right there. So because that carbon now has 4 bonds and the maximum number of hydrogens it could have in this case is only 3, it's obviously still known as saturated. The guy on the right is the exact same thing. He also, again, only has 1 hydrogen, 2 hydrogen, 3 hydrogen. And that's the maximum number of hydrogens he could put in there because this bond also counts for him as well. And that gives him 4 bonds, as we've been talking about, which is essentially what carbon wants to do. And we have the maximum number of hydrogens that we could put in there. So when we talk about saturated hydrocarbons, we're talking about organic compounds that pretty much have just carbon-carbon single bonds with the maximum number of hydrogens attached to those. And our basic organic sort of bonding, carbons attached to carbons, and then hydrogens attached to those carbons. Any questions on that there? So let's talk about really the simplest organic molecule you could have, and that is methane. It is basically one carbon and four hydrogens attached to it. Again, here are carbon hitting the maximum number of hydrogens it wants. 4 bonds and saturated here. These are a few different types of formulas. This is what is referred to as a space-filled model, oftentimes done on computers. This is a ball and stick model, which you would sort of build there, if you will, with a model kit. This guy here is the wedge and dash sort of situation drawing. The kind of wedge means it's kind of going behind the paper. The solid wedge kind of coming out of the paper, kind of like a three-dimensional sort of representation of the structure. This is what is referred to as the expanded structural formula. Expanded structural formula basically means we drew out all the hydrogens, as you can see here. Kind of like Lewis structures, we drew out all the hydrogens that are there. This is what is referred to condensed structural formula. In condensed structural formula, we don't draw out the hydrogens, basically. It's kind of similar to this guy without actually drawing out the hydrogens. So those are two very common ones that we commonly draw in organic chemistry, are kind of these two here, the condensed structural formula and the expanded structural formula. Now, let's talk a little bit about the geometry that we see here with methane and inorganic guys. If we go back to sort of our Lewis structure days here, and we think about the central atom, it has 1 electron pair, 2 electron pairs, 3 electron pairs, and 4 electron pairs, right? So 1 electron pair, 2, 3, and 4. It also has 4 bonds. So if you remember from Lewis structures and molecular geometry, something with 4 electron pairs has a geometry of tetrahedral. 4 electron pairs and 4 bonds has a geometry of tetrahedral. That is the 109.5 degree bond angle. And that's what we see here, that kind of 109.5 degree bond angle that we typically see in that tetrahedral arrangement. Any questions on that there?
Will the degrees always be 109, or do the degrees vary?
It will be, as we'll talk about here, in terms of alkanes, which are single bonded. And we'll talk about what happens to the sort of geometry when we don't have single bonds. We have maybe double bonds or triple bonds invoked. But typically in our carbon-carbon single bonds, you will always end up with that kind of 4 electron pairs, 4 bonds, tetrahedral arrangement. But as we go into different functional groups and different organic compounds, the geometry will change based on what's there in terms of bonds. Other questions? Okay, so this is ethane, which is actually the second organic molecule that you could have. It's 2 carbons and 6 hydrogens that are happening here. It is also a alkane. So methane's an alkane, ethane's an alkane. And this also are the different types of ways that we represent the formulas. Again, we probably in here won't be doing too much of these kind of drawings. Maybe in lab you might be doing maybe some of these type of drawings, but we mainly will focus in again here on our expanded structural formula. Again, we have drawn out all the hydrogens. This is our condensed formula where we did not draw out the hydrogens. Now, even though we write it like this, CH3-CH3, it is important to remember that the connection that's actually happening is the carbon to carbon connection here, even though it may appear like it's the hydrogen to carbon connection. We also should notice that as we went from CH4 to our C2, right? That we had to make this bond between the 2 carbons. And by making that bond, if you want to think about it this way, not necessarily correct what I'm doing right now, but if you want to think about it this way, if you put two methanes together, right, we really could not just slap them together because each carbon would end up with too many hydrogens and too many bonds, really. So when we make a bond, whenever we make a bond in organic chemistry, you typically got to lose two hydrogens. And what that does is it makes room for that bond to basically occur. Now that's a giant bond, but that makes room for it to occur, leaving carbon still with four bonds. Again, if we kind of try to throw both of those methanes together, the carbons would end up with obviously too many bonds in this case. A third type of structure or formula that we oftentimes will do is what's known as a line sort of structure. Line structure basically, is sort of a line that looks like this, for example. And it may just look like a line to you, but at the end of each of these lines, it is basically a carbon. And because carbon needs four bonds, everything else attached would be enough hydrogens to get yourself to four bonds for it. So sometimes we see line structures written, and we'll see some pictures here in just a sec. And again, it may just look like a line, but everywhere it sort of ends, everywhere a couple of lines come together, these are all carbons. So this is basically a carbon attached to a carbon, attached to a carbon, attached to a carbon, attached to a carbon. Also, again, because as I mentioned, carbon should have four bonds. The guy at the end has only one line coming in, which means he needs three hydrogens there. The guy right here has two lines coming in, which means he only needs two hydrogens. Guy right here has two lines coming in. He only needs two hydrogens to get the four, two hydrogens for this guy to get the four, and the guy at the end would only need three hydrogens to get the four. Obviously, the reason we don't usually put the hydrogens or carbons in is you can see it gets really messy looking. It's much cleaner just to look at it like this. And again, that's what each of those things represent when you see sort of line structure. Now, the question was about geometry. And again, if we look at this guy, which is ethane, we have the same situation happening: one electron pair, two electron pairs, three electron pairs, and four electron pairs. Going to be our same tetrahedral happening here. This carbon over here, also one electron pair, two electron pairs, three electron pairs, and again, four electron pairs there. Also going to be tetrahedral on that side as well. That tetrahedral geometry that we see occur in alkanes is why when we draw something in organic chemistry, and also why when we draw line structures such as this, we get what is sometimes referred to as the zigzag sort of shape. And that's because everybody here is basically rolling tetrahedral geometry. So you got that tetrahedral geometry. And what it ends up doing in terms of the shape of the molecule is it gives it that sort of zigzag shape, which is why, again, you see a lot of organic compounds really drawn that way. Any questions on that there? So looking at this here, we want to predict the shape around each of these carbons. And again, sort of to answer their other question, if we look at every one of these carbons, no matter which carbon we're looking at, because these are all carbon-carbon single bonds, they're all going to end up with four electron pairs and four bonds. And that's going to give each one of these that tetrahedral arrangement, which has that bond angle of 109.5 degrees in terms of its segment. If I wanted to turn this into, by the way, this is our expanded structural formula, what we got written here. If I wanted to turn this into a condensed, I would write CH3, CH2, CH2, and CH3. This would be the condensed structural formula. And where did I get all those things? Let me do it this way. CH3, that's a carbon and 3 C's, right? So that is where the CH3 comes from. Next to it would be CH2. That is a carbon and 2 hydrogens, CH2. Next one would also be CH2, which would be the carbon and the 2 hydrogens. And lastly, at the other end, there would be our carbon with 3 hydrogens coming from carbon, and 1, 2, and 3 hydrogens happening here. So that's how we go from the expanded structural formula to the condensed structural formula. In each of these cases, again, you can see carbon has made 4 bonds. Any questions on that? What would our line structure look like? Well, it would look something like this. And that would be it. That is the same thing as the other 2 formulas there. So if we look at sort of what we're seeing here, red is probably the bad choice. Do a different color. We'll go with yellow. So this guy right here is the CH3. Right here, this guy. This guy is CH2, which is this guy right here. This guy is the CH2, which is this guy right here. And this guy right here is the CH3 on this end. And again, all 3 of those things represent this 4 carbon alkane, which is known as butane. And again, top guy condensed structural formula, bottom guy expanded. And again, line structure on the right where, you know, it's pretty much just kind of bare bones, not too much going on there, just some lines. And again, really written in that zigzag sort of shape. Any questions on that there? Okay, so then let's talk about alkanes a little bit more officially here. Alkanes really are those simplest organic molecules that you could have. Again, the functional group really is, you know, some people call it a functional group, some people might not. But really the functional group is carbon-carbon single bonds. So you cannot have, the only type of bond you can really have in there is a carbon-carbon single bond. Can't have any double bonds, triple bonds, or anything like that. These are, again, what are referred to as saturated hydrocarbons in most cases, because they have all carbon-carbon single bonds. They have the general formula of CnH2n plus 2. So what does that mean? N is the number of carbons. So if I have 1 carbon, 2 times 1 is 2 plus 2 means I should have 4 hydrogens, and that was what we saw earlier. That is our organic guy known as methane. If I have 2 carbons, N would equal 2. 2 times 2 is 4 plus 2 is 6, which would mean I would have 6 hydrogens, which would be ethane. If I had 3 carbons, 3 times 2 is 6 plus 2 is 8. That would be what is known as propane. We saw just a second ago C4, which would mean I would have 4 times 2 is 8 plus 2 is 10. And that was our butane that we just saw. This, as we can see here, has 6 carbons. 6 times 2 is 12 plus 2 is 14. So that's the general formula for alkanes. For every 1 carbon, you know, basically, again, 2 times the number of carbons plus 2 gets you how many hydrogens you should put in there. Each of these are the molecular formulas for each of these guys. And again, you could draw any of those other ones as well. Any questions on that? So alkanes, as I mentioned, pretty much are those saturated hydrocarbons. They got only carbon to carbon bonds, carbon to hydrogen bonds. They are a continuous carbon chain, which means you could go all the way across with them. They also can kind of close up on each other and make more like ring structures, which we'll talk about as well. The way that we typically name organic compounds is what is sometimes referred to as the IUPAC name. That stands for the International Union of Pure and Applied Chemistry. Sad that I know that, but that was basically like the three guys that figure out how to name everything and really, mess with chemistry students. So they are the guys that come up with some of these weird rules we're going to talk about as to how you go about sort of naming organic compounds. Now, when we have alkanes, if you write out the name, end in ane. That's sort of the functional group. That's how they end. And that's exactly how alkanes end. They end in ane in terms of the last part of their name. So if you think about the names we were just talking about, methane, ane, butane, ethane, ane, propane, hexane, they all end up with basically ane at the end. That's how you can know if you see ane at the end, you're dealing with an alkane, you're dealing with carbon-carbon single bonds, and they should probably have the formula of CnH2n plus 2. Let's take a look here at the first 10 alkanes. This table, these names are so important here. You want to make sure that you get these names down. The reason why these first 10 names, formulas, and everything are extremely important is because pretty much every other organic molecule that we will name along the way, they all come back pretty much to these first 10 names. Every different type of organic compound, all the way through all the organic chapters, everybody pretty much defaults back to these first 10 names. You want to make sure that you learn these as soon as possible. It will make everything else a lot easier as we go through these organic chapters. So we've talked about some of these up to this point. That's one carbon, CH4 is methane. So we have our CH4, which is our methane, which we talked about. We had our C2H6, which is our ethane. We talked about our C3H8, which is our propane. Our C4H10, which was our butane. When we hit 5, we kind of go with the prefixes like it mentioned. So C5H12 is going to be pentane, like penta. C6H14 going to be hexa, like hexane. C7H16, hepta for 7, heptane. C8H18, octa, so octane, like gas. C9H20, which would be nonane, ANE. And C10H22 would be decane, like deca, for 10. Really important to know how many carbons, hydrogens there is. These 10 names, again, everything based off of it. Here are the condensed structural formulas. Again, not expanded, but condensed formulas. I will say that these line structures are off. So this one kind of goes this way, kind of down, across and stuff. So they're a little bit off from in this table. So this guy right here is actually ethane. And they're a little bit off like that. So again, there's not really a line structure for methane because there's only one carbon. So there's not really, if you actually draw the line like I did, that's technically 2 carbons and that's ethane. So really line structures will start with ethane. So it's just a little bit off in terms of that table. Any questions on that?
Are we going to need to memorize the line structures for these?
You will need to know line structures as well as, so those are the 3 sort of formulas that we will come across in this class. And that is line structures, condensed structural formulas, and expanded. For the most part, we'll probably do a lot of the expanded and condensed, but we will see some line structures along the way. So you do need to know probably those 3 for sure. Other questions?
Thank you.
Okay, so let us continue on here and talk about some of this stuff here. So we talked a little bit about the condensed structural formula, which again is a very common sort of formula that we do come across here in organic chemistry. And as I mentioned before, we do show the connection almost like the hydrogen to the carbon. So as I mentioned, it is really the carbon to carbon connection. So again, this being butane, if we really drew out all of the bonds, this is really what it looks like. Again, you can see the carbons are attached to the carbons, and we have our hydrogens there attached to our carbons. And this would be the expanded structural formula. This would be our condensed structural formula. And as I drew just a second ago, 1, 2, 3, 4 carbons, again, counting each of these spots, 1, 2, 3, and 4, again, would be the line structure. Normally, we don't put the little circles around it, but that would be obviously our line structure. Now, again, the expanded is really no more than just drawing out all the hydrogens. So drawing bonds, very much like what we did in Lewis structures. Drawing out these bonds is sort of what makes it the structural sort of formula. And here's our line formula. And again, we typically don't put any of these guys in. But again, just to show you in that line formula, the goal is pretty much that 4 number for carbon. And when we're kind of drawing things in organic chemistry and we're like, all right, I got a carbon here, what else should go there? It's always going to be hydrogen if it's nothing else. So again, it's assumed to be hydrogen, enough hydrogens to give each of these carbons 4 bonds. So this guy in the middle here would only need 2 hydrogens to get it to 4 bonds. This guy at the end will need 3 hydrogens to get it to 4 bonds. So that's really important in terms of remembering that number 4. And if you're not sure what should go there and there's nothing else sort of mentioned, it's almost a safe bet that it's hydrogens that are attached there. So again, like I said, these are really the 3 sort of formulas we'll see a lot. Definitely the condensed and expanded one we'll see a lot along the way. So you do need to be able to recognize, these different sort of formulas. Now, in addition, with our condensed formula as well, sometimes we get like a really big molecule where, I'll just kind of exaggeratedly draw here. We get something like this where, maybe you don't want to kind of draw out all these CH2. They're basically just repeatable units. So sometimes in the condensed formula, they'll actually kind of do this move where they'll go CH2 and 1, 2, 3, 4, 5, 6, and then CH3. So this is another sort of condensed formula way, and it happens a lot of times when we're dealing with something where it's a really long molecule. We have all these units that basically just repeat, and sort of a shorthand, instead of having to draw out of it all, put parentheses around that repeatable unit, the little number on the bottom to indicate that you got like 6 of those CH2s in a row. And that's, again, another very common sort of condensed formula way that we see. Any questions on that? Okay. So take a second here. Given this formula right here, write the molecular formula, do the condensed structural formula. Why don't you do the line structure as well? And why don't you name what the name of this guy is? So take a moment and see what you come up with. Look here. So first off, we want the molecular formula. You pretty much just count everything that's there. I see 1, 2, 3, 4, 5 carbons. So I know it's C5. By the way, I see all single bonds, which means I could count all the hydrogens, or I could just remember that that's an alkane, and it should probably have this formula here, which means in terms of hydrogen, I should have 5 times 2, which is 10, plus 2 more, which would be 12 hydrogens. And again, if I go through it, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So that would be the molecular formula. Any questions on that one there? Now, condensed formula, remember, is really just identical to this, other than we're not drawing out the hydrogens. So you might as well just start on the left-hand side, and I have a carbon that has 3 hydrogens attached. So that's going to be a CH3. I have a carbon with 2 hydrogens attached. That's going to be a CH2. I have another carbon with 2 hydrogens attached. That will be a CH2. One more carbon with 2 hydrogens attached would be a CH2. And lastly, on the other end, a carbon with 3 hydrogens attached would be a CH3. Any questions on that one? And that would be the condensed formula. Line formula is really just lines. We just need to get 1, 2, 3, 4, 5. And again, it's just going to be a zigzag move. So we're going to go up, down, up. If you're not sure, you can just count. That's 1, 2, 3, 4, which means I need to come down one more time for 5. And that is 1, 2, 3, 4, 5. That represents 5 carbons. And again, we don't draw the hydrogens on this. So the guy at the end would have 3 hydrogens. Guy in the middle has 2 lines, which means it has 2 hydrogens. The guy here in the middle has 2 lines coming in, which means it needs 2 hydrogens. Guy here has 2 lines coming in, which means it needs 2 hydrogens. Guy on the right has only 1 line, which means it needs 3 hydrogens. And that obviously would be our line structure. This last is when we name things, those first 10 alkanes are really important. It's all about the number of carbons. 5 carbons represents pentane, A-N-E at the end. Penta for 5, basically, pentane. Any questions on any of those sort of names or things?
I don't know if I'm looking at the chart one, the one that you previously had on, but the line formula, is there? I'm
Yes.
confused.
So again, like I mentioned, you're talking about this one, correct?
Yes.
Yeah. So again, like I mentioned in the book, or I don't know if it's in the book as like this as well, but at least in this slide, the line structures are off. So this first one's actually ethane, which is why I drew the arrow. And so of
Sorry,
course,
I must have said sorry.
that's okay. So this guy actually would be ethane. This would be propane. This would be butane. And this guy right here, which is sort of off, is actually right there. It goes there. So they're sort of off by 1. I think it just got shifted on the slide and stuff like that. There's really no kind of line structure for methane. And again, I don't know if in the book it's like that or not, but it just sort of shifted a little bit, each of those structures. Other questions on that? Okay. So why don't you take a second here and draw the condensed formula for ethane and heptane, and why don't you also do the line structure for it as well? Okay, let's take a look at how to approach this, and we're going to talk a little bit about how to approach this for a little bit more complicated things that you have to draw down the road here in just a little bit. And it's a good approach to do even maybe with something like this. Ideally, you would kind of know what these guys mean, again, when you learn those first 10 names, which is really important. Oftentimes, when you're given the name and you need to draw something like the structural formula, the condensed formula, whatever it may be, it's good to sometimes start with what is sometimes referred to as just like the carbon backbone. And what that basically means is when I see ethane, ethane should signal to me basically 2 carbons, right? And what I know is, again, since it's ANE, it's a alkane that is 2 carbons, and that means that I should have 2 times 2 is 4 plus 2 more is 6 hydrogens. What I mean by starting with a carbon backbone is simply just, drawing 2 carbons. That's a good way to kind of start it. We know that they're going to be attached to each other. Again, may not be that big. Now, remember the idea that carbon needs 4 bonds, right? And if there's nothing else there, those bonds are going to be hydrogen. So if I look at the carbon on the right, it has one line coming in, which means to get to 4, it needs 3 more things, and those 3 things would be hydrogens. Looking at the carbon on the left, it has one line coming in. To get the carbon on the left to 4, it also needs 3 more hydrogens, and that would be my condensed structural formula. Line structure in this case would actually just be something weirdly looking like that. Again, a carbon at each end with 3 hydrogens at each end would be our line structure. Question on that one. Hepta means 7 carbons. So again, if you just start with 7 carbons sort of drawn as like your backbone, and again, this is a good way to do more complicated guys as well. 3, 6, 7, lay up as a bond to each of them. And again, you could pretty much get counted. The guy at the left end has one line coming in, which means to get him to 4, he needs 3 hydrogens to get to 4. Now by doing this, I can see the carbon in the middle has one line to the left, one line to the right. That's 2 lines, which means to get him to 4, he actually needs 2 hydrogens. Same thing with the carbon next to him, has 2 lines coming in. We'll need 2 hydrogens. Same thing with the guy next to him, 2 lines coming in, needs 2 hydrogens to get to 4. Same thing with the guy here. Perhaps you see a pattern developing here. Same thing with the guy here, needs 2 hydrogens. Guy at the end has 1 line coming to it, which means he needs 3 hydrogens, and that will give us our heptane. Our line structure would be 7 of these guys. So 1, 2, 3, 4, 5, 6, and 7. If I didn't screw it up, 1, 2, 3, 4, 5, 6, 7. Question on any of those? And again, you could also put the 7 into the formula here. And that would tell you, again, if you weren't sure, 7 times 2 is 14, plus 2 more is 16. 3, 5, 7, 9, 11, 13, and 16 hydrogens all the way across there. Any question on those 2? So these are what are sometimes referred to as straight chain alkanes. They're straight chain, which means they pretty much just run straight across. These are, again, straight chain. And that's different than, as we will see down the road here, what are sometimes referred to as branched chain. What is a branch chain? Well, it's like a tree, right? A tree has branches. There's like a main sort of, sort of part. And then off of it is some branch work kind of happening, other things coming off the end of it and stuff like that. So when we talk about alkanes, we sometimes talk about straight chain, which is straight across. Everybody just runs straight across. Branch chain means, off of the main part of it, there's like a tree, branches of different things coming off of it. Another sort of class of alkanes are ones where basically the 2 ends of the alkane basically come together and join. And they come together and join and form what are referred to as cycloalkanes. Cycloalkanes are ring type structures. And they're really a result of like these 2 guys deciding we're going to come together. Now, if you remember, we talked about at the very beginning that every time we pretty much make a bond in organic chemistry, we need to kind of sacrifice 2 hydrogens, right? And that's what you see when this guy closes up on each other. Instead of 3 hydrogens here, he has 2. Instead of 3 hydrogens here, he has only 2. And that's because we need to get rid of a hydrogen on each carbon to make room for that bond to form. And otherwise, we would have too many bonds to carbon. So cycloalkanes actually have the formula of CnH2n. So for example, down here is 3 carbons. So that is this guy, 3 carbons. And when we close it in on each other, these cycloalkanes make our nice geometric shapes, like a triangle. This also has 3 carbons, but there's basically only 2 hydrogens at each of these spots. Again, because there's 2 lines coming into each of these carbons, giving each of these carbons now 4 bonds. So C3, 2 times 3 is 6. So 3 carbons, 6 hydrogen. How do we name these? Well, we simply put cyclo in front of it. So propane becomes cyclopropane. If we have a square, which is a common one, square has 1, 2, 3, 4 carbons. A straight chain with 4 carbons is butane. This ring structure of it is cyclobutane. And you can do that for pentane is another common one. This is cyclopentane. Again, 1, 2, 3, 4, and 5 carbons. And cyclohexane, also a geometrical shape, 1, 2, 3, 4, 5, and 6. So these guys typically will be drawn in line structures a lot of times because they have these sort of geometrical shapes. They're oftentimes drawn this way. But again, if we looked at something, if we get down here, there it is, like our cyclobutane, it would be something like this. And this would be the condensed formula for, this would be condensed for cyclobutane. This would obviously be the line structure without the little circles at the corners. And then expanded would be, you know, everything drawn out basically, you know, just like this. And that would be expanded structural formula for cyclobutane. So we name them the exact same way. The simplest sort of cycloalkane you could have is 3 carbons because that's as best as you get at. So it starts with the triangle. And we just simply put cyclo in front of the name. Any questions on that one there? Okay. And here's a table for your book that sort of does that. And then, like I said, a lot of times, this is the condensed structure for each of these, but a lot of times these will be drawn in line structure. Again, it just gets a little crowded trying to do all this stuff sometimes. So for simplicity, a lot of times people will apply more of the line structure, especially the cycloalkanes. It's a very common sort of thing. All right, take a second here. Why don't you name each of these and we'll talk about it. And as we'll talk about here, it's really all about how many carbons. And a lot of times the base of most names are how many carbons in a row, the longest continuous carbon chain. It's a very common theme in terms of naming. You always look for that longest continuous carbon chain. We have nothing else attached here, so it's pretty straightforward. Pretty much just need to count. So that's 1, 2, 3 carbons, 4 carbons, 5 carbons, 6 carbons, 7 carbons, and 8 carbons. 8 is octa, and this is octane in that particular case. Nothing else attached. Again, all the red circles I just did are carbons. Attached to each of those red circles are basically hydrogens, enough hydrogens to give each of those carbons 4 bonds. So 2 hydrogens in the middle, 3 hydrogens at the ends. Any questions on that one? Same thing here. We want to count. So that's 1, 2, 3, 4, and 5. That is pentane, which is 5 for penta. But this is a ring structure. So we're all attached all the way around. So that is the guy that will then get cyclo in front of it. And this would be cyclopentane. Question on that. Just 2. Coming through here, we'll just go through these together since it's kind of similar to what we've been doing. Again, it's all really about counting the carbons. So 1 carbon, 2 carbons, 3 carbons, 4 carbons. They're all continuous in a row. There's absolutely nothing else attached. So 4 carbons is butane. Here again, counting the carbons, 1 carbon, 2 carbons, 3 carbons. 3 carbons is propane from that list. Again, it is not a straight chain, but kind of wrapped up in a ring. So we would add cyclo to the beginning of it, and this would be cyclopropane. Coming down here in our condensed formula, 1 carbon, 2 carbons, 3 carbons, 4 carbons, 5 carbons, 6, 7, and 8 carbons all in a row. 8 is octa, which becomes octane in terms of this guy's name. And lastly, I kind of jumped the gun on this guy just a second ago, but we have 3, 4, 5, and 6 carbons. Again, hexa is 6. So this is hexane. It is not the straight chain hexane. It is 6 carbons all attached in a ring type structure. And that would then make it cyclohexane. Any questions on how to name simple organic alkanes here? And it is really about naming the longest continuous carbon chain is what you're looking for. Longest means doesn't have to be straightest, as we'll see in just a second here probably, but you just can't go backwards. So once you start at one direction, you keep counting until you basically hit a wall, and you want to look for the longest continuous carbon chain. Are you asking would this one be cyclooctane? Is that what you're asking? No, the cyclo is for ring structure here. So the sort of ring structure basically means that you take like a straight chain guy.
Oh, I'm just asking if that's how we'd spell it, or do we like drop it now?
Oh, okay. I'm sorry. Yeah. So you would probably keep it. I don't think it would run across it too much. Usually we kind of top out in terms of the cyclos to here, but you would probably name it like you wrote it there then in that case, yeah. But usually cyclohexane is kind of the biggest sort of cycloalkane that we come across in most cases. But technically speaking, that's what you would do, yeah. You just put the cyclo in front of it, and you probably wouldn't drop the O. Other questions?
I do have a quick question, and I may have missed it. I'm sorry, I had some other things going on. But on the cyclohexane, when you draw it in condensed structure formula, how? Because I noticed like part of it is H2C, and then the other part is CH2. How do you know, like, when you're setting it up? How do you know which formula to put where?
How would you do the condensed formula for D? Is that what you're asking, basically?
Yeah, because
you'd probably do it like this. So in most cases, people would probably do it just like this. And again, with the condensed formula, it's sort of implied, even though sometimes it appears that the connection is like the H to the C, like here. Most people are probably okay with it. If you find somebody that's maybe not okay with it, you might even see people kind of just draw it like this, but put the H's on the outside, if you will. So sometimes people kind of do it like that as well, just to kind of apply that. But there's really probably nothing wrong with the top one. But sometimes people try to maybe do it like that. But even on the bottom, you're still going to kind of run into a problem of that. You're going to have something kind of like that. So, for the most part, this would be how you would do it. And again, even how we're connected here, even though it sort of implies that the hydrogen is attached to the carbon, it's really not. And it's understood that it's not. Again, like sometimes people might even write it like this to try to do that. But again, the guy in the middle, you got nowhere really to go with him, so that H to the C is going to kind of look like it's being attached that way. So you'll see some variations on that, but most people in terms of the condensed form are okay, just kind of rolling straight in like this. And again, it's just understood that that connection is between the carbon and not really the carbon and the hydrogen, even though it kind of looks like it is.
Okay.
If that was your question. Yeah.
Yeah.
Okay.
Thank you.
You're welcome. Other questions?
Yeah. So with
to D, will
D.
the molecular formula for it would just be like C6 and then H 12?
Yeah, so it would just be that. So so each of these have 2 hydrogens. So yeah, it would just be like C6H12 would be the molecular formula for it. Yep.
Okay, will there ever be a problem where you give us the molecular formula and then we have to like draw it out?
You may, and it would be probably more so something like it would be probably more so something that's maybe just the alkane by itself or something like that, like C2H6 or something like that. So it's possible, yeah.
Okay.
But you would have probably some idea. You would have some idea of for example, if you were given this formula, you would know it wouldn't be just a straight 6 in a row, because that would be basically this many hydrogens, right? Because it has this CN H2N plus 2. This guy is lining up more like the CN H2N, right? 6 hydrogens, 6 carbons, and 6 times 2 is 12 hydrogens. So that would give you an indication that, maybe it is a ring type structure, is probably just not the straight chain because it's missing 2 hydrogens from the straight chain. So there are some clues that sometimes you would come across, but it is, I guess, potentially possible to be given just the molecular form. It has to draw something. Yeah.
Oh, okay, thank you. That makes sense.
Okay. Other questions? Okay. Then let's get into some of this stuff. Let's talk about what happens when we start adding some things to this and some other important things. So when we do get alkanes that have what are referred to as substituents, these are sometimes what are referred to as branch chain, as I was talking about. And here's our straight run of 4 carbons in a row, and that is our butane, right? If we look here, this also has 4 carbons. It also has 3, 6, 9, 10 hydrogens. This guy again also has 4 carbons and has 3, 6, 8, 10 hydrogens. They are both the exact same molecular formula, as was sort of the question just a second ago, right? They both have the exact same molecular formula, but they actually do have different names. This is a straight chain alkane. This is a branch chain. So what I was talking about before is we got this kind of branch coming off of it. How do we go about naming each of these? Well, the first guy is pretty simple. We do what we just did. There's 4 carbons in a row, and that is butane. When we name things in organic chemistry, as I mentioned before, what we are looking for is the longest continuous carbon chain without going backwards. Okay, so you go one direction until you can't go any further. If I look at this structure, that is 1, 2, 3 carbons in a row, and now I cannot go any further. Does the longest continuous chain has to always be the straightest? It doesn't. What happens if I went 1, 2, and then went up? That is also 3. So when you have a structure that you need to kind of figure out the name, you always want to find the longest continuous carbon chain. So that's really the first step that what you want to do is find that longest continuous carbon chain. In our case, it is 3 in this case, right? For that guy, 3 carbons. No matter which way you go, there are 3 carbons. When you have an option, it's probably best just to kind of put a box or circle the straightest. All right. That longest carbon chain, which in this case is 3, is really the base of the name. So 3 carbons, as we talked about earlier, the base of the name will be propane, right? But there's still something else attached there that is attached to that main chain. And that is this guy up here, this sort of 1 carbon unit, which is what is referred to as sort of the branch part of it. That little guy right there, that's not part of the main chain, but that's attached. That is what is known as a substituent. It is basically what is known as a group that's attached. and it's actually known as a alkyl group. What is that group that's attached? Well, that group that's attached is 1 carbon and 3 hydrogens. Now, you might look at that and go, that looks very similar to our alkane that has 1 carbon, but it has 4 hydrogens. That's methane, right? Now, in this case, we don't call this methane because we cannot throw methane onto my green part. The reason we cannot just throw methane onto my green part of my structure the way it is if I did, I would be attaching methane like that. Now this carbon has 1, 2, 3, 4, 5 bonds. Not good. So an alkyl group is also based off of those first 10 names. So again, hopefully you're starting to see that those first 10 names are really important. The groups that are attached here are also based off of those first 10 names. This has a 1 carbon group, but it's missing that 4th hydrogen. Why is it missing the 4th hydrogen? It is that extra part that's missing that allows it to connect to the main part of the structure without giving carbon too many bonds. These are what are known as alkyl groups. Surprisingly enough, alkyl groups end in YL. Methane then gets rid of the ANE, and this is what is known as a methyl group. YL at the end, surprisingly enough, because this is an alkyl group. This would be known as methyl propane. Not only is it known as methyl propane, but naming is all about telling people exactly where you could find everybody. That means that we want to number our carbons. So if we look at our carbons here, I'm going to draw a little bit bigger over here. We can number this carbon in one of 2 directions. We can number the carbons on the main chain by going left to right. This would be carbon 1. This would be carbon 2. This would be carbon 3. We could also number that main chain going in the opposite direction. This would be carbon 1. This would be carbon 2. This would be carbon 3. In this particular case, it does not matter which way I go. This group is attached to carbon number 2, no matter which way you go. This is why this would be known as 2-methyl propane. The 2 indicates that the methyl group is on carbon number 2. The propane indicates that the longest continuous chain has 3 carbons attached. Any questions on how we got to that name? So when we're naming, we want to go with the longest carbon chain. We want to identify the groups that are attached. And we want to number the chain. And the importance of this is we want to number the chain to give the group the smallest number. In this case, it did not matter, but we always want to go smallest number when we're numbering that chain to give kind of the group the smallest number. And in this case, either way, it was 2. Any questions on that? We're going to obviously do more naming here in a bit, but any questions so far? Now, coming back to what we're looking at, they both have the exact same molecular formula, but they have different names. One is 2-methylpropane, one is butane. These are things that are related to each other. These are guys that have the same molecular formula, but a different connection. And those are what are known as isomers. So isomers are really structures that have the same molecular formula, but different arrangement. And that's what these 2 guys would be. They are isomers of each other. They have the exact same structure, exact same molecular form, but different structure. Now, a very common mistake that people sometimes do, if they're asked, hey, draw some isomers, they will sometimes do this move. And go, cool, I just drew an isomer. Definitely looks different, but is it different? And let's see how we could determine if it's different. We got 4 in a row here, longest continuous chain, that is butane. If we count the carbons in a row here, 1 carbon, 2 carbons, 3 carbons, 4 carbons, that is still 4 carbons in a row. That is also butane. They have the exact same name. These are not isomers of each other. This is just somebody drawing it down, thinking that changed anything. So a very good way to recognize whether or not you actually drew an isomer or not is to actually name all the pictures that you drew. If you named all the pictures you drew and you ended up with different names, you probably drew isomers. If you named these pictures and you end up with 2 guys that have the same name, they're not isomers of each other. You probably just did something very much like what I did here. And that's a very common sort of error that people do. They just kind of, I'll just draw like this side up and this side down. It looks different. So it must be an isomer. Any questions on that? Okay, so let's finish up kind of looking at sort of this idea. And again, as to the earlier question, this would be a case where you would be given just a formula and you're asked to draw 3 different isomers for pentane. So how would you go about doing that? Well, you might as well just keep it very simple and go 1, 2, 3, 4, and 5 in a row. Remember now, everybody else is, 2, is going to be hydrogen here. So this guy would obviously be pentane, right? It is 5 carbons straight across. All right, so now I need to draw some other arrangement. Well, a good move would be perhaps instead of 5 in a row, maybe I only go 4 in a row. And then I attach a carbon up here. That is now 5 carbons. I filled the rest in with hydrogen. That gives me 2. That gives me 1. That gives me there. That gives me there. Maybe I don't go 4 in a row, but I only go 3 in a row and throw a carbon up on top and maybe a carbon up on the bottom. And again, filling in my hydrogens. I would need 3 on all my outside ones. The guy in the center does not need any hydrogens. It has 1, 2, 3, 4. Maybe I decide I want to do this. And fill in here my hydrogens. Every single one of these guys that I drew has 5 carbons and 12 hydrogens. Let's see if I did isomers on all of them. If I come across here, longest carbon chain is 4 carbons in a row. 4 carbons in a row is actually butane as the base of the name. I have a group that's attached here. That's a 1 carbon group, which would be a methyl group. That would be methyl butane. Now I can number this 1 carbon, 2 carbons, 3 carbons, 4 carbons. I could also number this 1, 2, 3, and 4. Which way should I go? I should go this way. Why should I go this way? As I mentioned just a second ago, we want a number in the way that gives the group the smaller number. 2 is smaller than 3, right? So this would be 2-methylbutane. So that is a different name. So those 2 are isomers of each other. If I come here to my bottom guy, there's a few different ways I could get there, but I'll just go straight. Straight across is 3 carbons. Now 3 carbons is the base of my name. 3 carbons is propane for my 3 carbons. I now have one group attached here, which is a methyl group. I have one group attached here, which is a methyl group. That is 2 methyl groups in the same molecule. When we have 2 of the same groups in a molecule, we use a prefix. Prefix for 2 is di. This would be dimethyl because there's 2 methyl groups attached here. Where is that methyl group located? Carbon 1, carbon 2, carbon 3. If I go the other way, carbon 1, carbon 2, carbon 3. It doesn't matter which way I go. Each of those groups are located at carbon number 2. Also important in organic chemistry is to give the number for each group. So I would do 2, 2, because each of the methyl groups are on carbon number 2. Dimethyl propane. Again, a different name. It is an isomer. So all 3 of these that I drew on the bottom are isomers because I could really double check it by naming them, and I got different names. What about the guy at the top here? And I'll end it. I know I'm a little bit over. Let me just end it real quick here. Now, the guy up here on top, longest carbon chain is 4 carbons in a row. 4 carbons in a row is butane. Has one group attached, which is a methyl group. This is methyl butane, right? Where is that group really attached to? Again, when we number the chain, there's 2 ways you could do it, left to right, 1, 2, 3, 4, or right to left, 1, 2, 3, 4. The smallest number would be 2 in this case for this group. 3 would be going the other way. That means this is 2-methyl butane. Wait a sec. That is the same name as what I got below. That means although it may appear to you to look different, it's actually the same structure as this guy. And that's why it's really important when you do isomers and you draw these different structures to go back and name them, because this would not be another isomer. It's actually just the same picture as I drew here. So it does happen a lot when people do isomers. They kind of just move things around, flip things around, and they think they're drawing something different, and it's really not. And that's the best way to sort of figure out whether or not you did actually draw something different, is to name it. We obviously will do more practice of naming next time.